We have very intriguing talk today. I don't see the title here. Here title's a little bit downsided, but the original title was Why Anyone Would Use Graphite in Nuclear Applications, and which sounds very, very nice for the opening seminar. And the speaker today is Dr. Will Wines. Dr. Wines got his bachelor degree and master degree in nuclear engineering, a bachelor degree at UC Santa Barbara, and a master degree at the University of Illinois, and PhD at the University of Idaho in material sciences. Currently, Dr. Wines is a researcher at Idaho National Lab at the high temperature reactor graphite research and development technical lead. And he was working on this issue for 10 years, so we will find out everything today in one lecture. Thank you very much.
Thank you very much. Thanks. So, yes, I am Will Wines from the Idaho National Laboratory. I am the HTR Graphite R&D technical lead, or as I like to say, the graphite geek in Idaho. I want to thank everybody for showing up on a Friday, especially for talking about something that probably a lot of you are like, why are we talking about this? I also want to thank the organizers for bringing me here. It's a quite privilege for me. So yes, today I'm going to talk to you about nuclear power, and specifically about nuclear reactors. It's a little bit different. When I say nuclear reactors, people hopefully think about this nice beautiful sky, nice green pastoral setting, this dome-like fixture, these large cooling towers, and nice pastoral type of concept. Or possibly, again, you got these containment buildings, no cooling towers because it's coming directly from the ocean. This is my personal favorite. I worked at San Onofre Nuclear Generating Station, which is what this is, when I was approximately the same age as many of you here in this room. Hopefully some of you won't remember this. This is 3 Mile Island. This is Unit 2 over here, which has been decommissioned because of the 3 Mile accident that probably everybody in the room has heard of. This is Unit 1, still operational, right next to it. And again, look at those cooling towers. And if you haven't seen all those pictures, you've probably seen this. All right. The interesting part of that is that all of these things are light water reactors. All right. 100% of the power that's produced, nuclear power that's produced in the United States, is by light water reactors. Primarily, it's a remnant, and a purposeful remnant, from our Defense Department. Because of the nuclear Navy, we've taken their technology and we've used it. Why spend billions and trillions of dollars looking at another technology when you have this perfectly great technology? So that's what's happened here. And so what you have, what's really interesting, is most people focus on those gigantic cooling towers. Well, the business end is actually inside these concrete reinforced domes that a 747 fully loaded impacting would make a dent about this big on. That's because there's controlling this canister that's about 10 feet in diameter, about 25 feet long, and it's got the nuclear fuel in it. It heats up the water, it comes over, heats up more water over here as it makes the primary circuit, comes over to the turbines, which generate the electricity and powers your little city over there. All right? I'm not going to go into any kind of reactor design because I'm not an expert in that, but that's what light water reactors are doing, and they are fabulous at it. They really are. For the past 50, 60 years, we have perfected the energy generation with light water reactors quite well. Now, today, what I'm going to talk to you about is a high-temperature gas-cooled reactor. Same concept. You have a nuclear heat engine, which is heating up a coolant. But in this case, the coolant is actually gas. All right? And for graphite, you want an inert gas because obviously you get oxygen and hot graphite in the same room together, and they kind of react a little bit, and they have a little bit too much fun together and turn into CO and CO2. Again, it comes back in and it heats up another coolant, gas, molten salt, water, you name it, I don't care. And then that can be used in different processes because the reason that we want to do this is a new design, not really a new design, it's an old design that's now brand new, is because it's the very high temperature, 3 times the heat that you normally get out of a light water reactor. Right? So now instead of 300 degrees C, which generates enough energy to go in and boil water and create steam that pushes turbines. Now you're talking 1,000 degrees Celsius. Now you're starting to look at things that can start to assist in the melting of steel. You're looking at chemical processes that no way that the pressurized water reactors or the boiling water reactors could ever get to those kinds of temperatures. This is what these reactors are designed for. When I first started, it was to produce hydrogen. Anybody in this room who remembers George Bush Sr., who wanted, and Jr., who wanted that hydrogen economy, the Freedom Car? Anybody remember that? If you do, you're probably as old as I am. The rest of you, not probably. We can do that because we have the high temperatures capable of going in and cracking water, as well as going in and doing something like a sulfur iodide process. Graphite, like I said, it's an old concept that's brand new, or being dusted off for brand new. As I said in my opening abstract, Enrico Fermi used this for Chicago Pile 1 to create the first nuclear reactor. And since then, we've had well over 100 graphite reactors built throughout the world. In fact, graphite reactors are quite common in most of the world. It's only in the United States where we've kind of been sort of homogenized with light water reactors. In fact, in the UK, all of their nuclear, almost all of their nuclear energy is produced by graphite-cooled or graphite-cored reactors. They use CO2 instead of H2O, or HE, So we've got quite a history of using graphite from the very first reactor to be one being built right now in China, and it's one of 15 that they plan on building. So does Japan, so does Korea, and Japan is helping, I think, Kazakhstan design and build one as well. All of these types of reactors are being built other than the United States because, why? Because we have more oil than we know what to do with because of fracking. All right, we don't need that kind of a technology as much as the rest of the more fossil energy deficient folks. As a consequence, they need this kind of advanced technology. And that's why this is so popular. All right, when I talk about graphite reactors, this is what I'm talking about. These things are about 1 meter tall. For those of us still stuck in the ancient English metrics, this is about 3 feet tall. They're about 18 inches or 1/2 meter in diameter. And what you have are hundreds of these things stacked close together. And then they're like Lego pieces. We just stack them 10, 12, 14 tall. This blue area right here is basically the fueled region. That's where you stick the nuclear fuel. That's what gets hot. Half of these holes are where you stick the fuel in the form of a uranium oxide carbide particle. There's billions of these particles inside the reactor, and they then get capped, put into these places. This heats it up. These reflector blocks go ahead and reflect the neutrons and moderate it. Okay? So that's what I'm talking about. When I talk about nuclear components, I mean this. This is the entire interior of these reactors. It's filled with graphite. Okay, this is the concept for the NGMP. You got this reactor, pretty small, goes in, high heat comes out. Some days it generates electricity. When there's solar power, wind power, or some other renewable energy source that's heating up or lighting up the city or doing whatever needs to, you switch it over to a hydrogen production or chemical production plant. That was the original concept. Why? Well, because, like I said, light water reactors, your 300-degree outlet temperature, it's about 1,000 for a graphite core. The fuel, and I'm stretching back to my nuclear engineering days, but I think the fuel at the cladding is 400 to 600 degrees C. Graphite core operates at above 1,000 degrees normally. This is the big one, though. The structural support can go up to 3,000 degrees Celsius. That's what normally graphite is processed at. That's how it's fabricated, is at 3,000 degrees. It's capable of sitting there and holding on to itself. Basically, doesn't melt, doesn't do anything, and up to 3,000 degrees C. No way would you ever want any kind of component in the light water reactor even approaching the 1,500 degrees for an off-normal or accident scenario. Fukushima is a good example of why you don't want to do that. So why do we want to use these things? They're thermally stable. There's just no melting. These things are effectively indestructible in many ways. All right. The second thing is that they are passively safe. They shut down naturally. Now the new generation 3.5 and the concepts for the generation 4 light water reactors, they're passively safe too. They use something in the same negative temperature coefficient of reactivity that the graphite does. When the graphite gets too hot, it vibrates too much, the atoms vibrate too much, they cannot thermally moderate the neutrons. It can't slow them down. It literally stops the nuclear reaction until it actually cools back down. In fact, when I graduated from Santa Barbara, I went to the only graphite operator and graphite reactor operator in the United States, and I begged them for a job because I did not want to go to grad school. And they said, we'd love to hire you, kid, but we're going to shut this place down. And the one thing that they wanted me to do was to tell the NRC that when there was an accident, they wanted the reactor operators to get up out of their seats, take 3 steps back, and sit down and leave it alone. Because the only thing that could screw it up is humans. So that's one of the things that we have to, that makes these things so attractive. You can park them next to chemical processing plants that explode, and this thing will sit there and take it. Theoretically. I don't think I want to be around when they do it, but, you know. Okay. So what do? I've been working for the last 10 years or so on the NGMP, the VHTR program. Basically what I do is I look at this, trying to define and understand the safe working envelope for all nuclear graphite. It doesn't matter if it's gas-cooled reactor that we're talking about in the United States. This is the Chinese HTRPM. This is the molten salt reactor concept where they, instead of use helium, they use molten salt to cool it down. Or you can use the advanced gas reactor like the UK has over there. It's all graphite. It all has pretty much the same issues. What are the issues? They break down into 3 areas. Property changes from irradiation, degradation mechanisms, and fission product transport. I threw this one in because it's not really something that I'm concerned about, but boy, the fuel guys really are. Because if we can show that the fission product hangs up in the graphite during even an accident, then the release rates are significantly less, and they have much, much less of a problem in any kind of an accident scenario. And that's a big, big deal. Okay, so let's jump right in and talk about the issues, because like I said in my abstract, what I'm trying to do is give you an understanding, a flavor for what the issues are for graphite. The first one is the biggest one. It's the dimensional change. And graphite is this weird material that under irradiation it actually starts to shrink, physically, volumetrically shrink. It then stops, what we call turnaround, and then it starts to swell. Okay, well that doesn't make a lot of sense because most things don't shrink under irradiation. So what's going on? Okay. Also, graphite's not really, made out of rubber. So how can something literally shrink down and then expand back up without tearing itself apart? Okay, it's a quasi-brittle material. That doesn't make any sense. What's even worse is that from the dimensional change, it's dose dependent. So the more dose, the more dimensional change happens. So what you see is that anything that's right next to the fuel starts to go in and compress immediately, leaving the other stuff behind it in a state of great internal stresses. Then it gets even worse. Once it hits turnaround, when the blue starts, this starts to become tension while this is in compression, and pretty soon everything just goes to hell in a handbasket. And you see that right here. This is past turnaround where you actually have cracks forming and large voids forming in the microstructure of the graphite itself. It's literally tearing itself apart. This is shown in charts. I have removed all equations from my discussion. I see lots of smiles. I like that. But I do like pretty pictures, especially multicolored ones. So what this just shows you is that this is the dimensional change. It shrinks and then it expands back up. You can see they're not mirror images of each other, and I'll get to that in a minute. The different colors just mean different temperatures. It starts to turn around faster at higher temperatures. And I'll show you why in a minute. DPA, I'm sorry, that is a displacements per atom. It is a unit of measure of dose, or the amount of neutrons that have been received by a material. What this means is that if you had 1 DPA, that means that every single atom in that material has been displaced from its atomic lattice at least once. That's what it means. So, from a dimensional change, it's huge, large internal stresses, fracture and structural problems, and then, of course, if they break, you got a control rod insertion issue, which the UK is talking about. You also have gas gaps between the components. Okay, instead of actually going down and cooling the fuel directly, you may actually have stuff that's opening up, breaking, and allowing the gas not to cool the fuel. Big problem. Heat conduction through the core, again, is a problem if you interrupted the gas flow. And then I haven't talked about irradiation creep, but for those of you metal guys, creep is actually good in graphite. It's a misnomer, and I'll get to that in a minute. But basically what it does is that's what relieves the stresses and reduces the fracture potential. Strength is another one that's really weird. It slightly increases about 10-15%, and then it just drops off. I'll get into that why in a minute, but basically increasing the strength, you know, it helps the dimensional change and reducing the fracture because it's stronger and it's just going to reduce it that much. But it's complex. You need a biaxial stress response and the flaw evolution because as I showed you, you've got cracks forming, you've got voids forming towards about the middle of that irradiation curve. How does the fracture response respond to that? Okay, this is my crude attempt at my cartoon figures here. Don't laugh at them. From irradiated graphite, it's very high conductivity or diffusivity. So it gets rid of the heat very quickly, which is great. You want to cool down the fuel so you don't get it over hot so the fission products aren't released. You need to cool the fuel down. That's what the graphite's job is there for, to protect the fuel. It does it by keeping the heat away from it. If it doesn't, Fukushima happens, 3 Mile Island happens, and Chernobyl happens. The only reason those things were, we had a problem with them is because we couldn't get the heat away from the fuel. Chernobyl had a few other problems, but that's the Soviets' issue. Because of that, you have this large heat gradient. It's able to take the heat out quickly. And again, it cools the nuclear fuel, if you want to think of it the opposite, rapidly. Thermal conductivity, unfortunately, drops rapidly in order of magnitude. About the first neutron it sees, it just drops out of the bottom. As a consequence, it has a small heat gradient, and this heat stays near the fuel. And it's not a big issue when the reactor is actually operating normally, because we can take account of that and we can design for it. The problem is once you stop the coolant during an accident, and that heat stays in there and it doesn't get out of the core. That's a potential problem. We'll talk about that in a minute. Again, just a chart showing the precipitous drop even at a very low amount of irradiation. And one of the things that I wanted you to see right here is that when we're talking about the operating temperature of 1,000, 1,200 degrees, just simply due to the thermal interruption of phonon transport, the irradiated and the irradiated actually match. So like I said, at the normal operating temperatures, it's not that big of a deal that you have this irradiation drop in the thermal annealing. Thermal diffusivity. What you have a problem with is when you're starting to get into the 6 to 5 to 400 degree range where graphite still can oxidize, and if you've got air coming in, you can have a potential problem getting that heat out quickly enough. Thermal expansion, again, basically what you're looking at is, remember the gaps between those stacked up stacks of the graphite columns? They're pretty small. They're like a couple of millimeters, 3 to 4 millimeters. The expansion can give you a bit of a problem. It's kind of secondary in nature, but I threw it in. Degradation. When I talk about degradation, I talk about oxidation of the graphite core. So you got air, water ingress, basically oxygen, hot graphite mixed too well. You've got two basic scenarios that I'm dealing with, which is one is you break the main hot duct. Helium rushes out, air rushes in, and this stuff is still hot. When I mean hot, I'm talking 1,500, 1,600 degrees hot sometimes. So what happens when you have that kind of temperature and you mix it with air? The other one is a small leak. All of a sudden you have a small leak, you have a heat exchanger and a water heat exchanger that kind of comes in and leaks in a few gallons of steam in this thing, and it cycles through the reactor during normal operations. That happens all the time. For every single graphite reactor, you have water leaks. And they're small, and the graphite deals with it, but it's going to erode over time. So those are the types of issues. For a catastrophic acute, you can see within a few hours at 100% air, there's no mixing of the helium or CO2 or anything else. This is the worst case scenario. Within a few matters of an hour or 3 hours or so, you've got 10% mass loss, which can equal roughly, about rule of thumb, 50% strength loss in your graphite. That's a big deal when you're talking about 100 metric tons of graphite, which is sitting there being held up by graphite columns. It could settle down. We need to understand what the rate is and figure out how to mitigate that. Fracture, we're looking at scratches, large defects, chips, cracks. University of Minnesota has been working and trying to look at voids inside the graphite. These are engineered pieces of graphite, folks. We don't just cut them out of the ground like limestone or marble or anything. We actually manufacture these things, and as a consequence, you can get voids, cracks, you name it inside those things. And we need to have an ability to figure out what these will do to the fracture, right? Because we don't want these things to fracture. And finally, the fission products. As I said, will the fission products hang up if they're released from the fuel? What's the effective diffusion rate? This significantly affects the safety case and safety envelope of the fuel. Okay, what's going on? So this is where I try to explain to you what's going on. Why does the graphite shrink then expand? What's the dimensional change? Why is there an increase in strength? Onward. I'm going to try to give you some answers, but not all of them, because obviously I don't know, and there's a lot of people who don't. But I can say this. Graphite unique structure is the key to most of the weird things that it does. It's an anisotropic material at the crystallite level, all right? It's these perfect graphene planes that are bonded weakly with van der Waals forces between them. They're strongly covalent with weak van der Waals. That gives it a highly anisotropic structure. Okay, that starts off by this benzene-like ring, which we then form into hexagonal ring, which then comes into this chicken wire type basal plane, if you will, or graphene type plane, and then they stack these things up, AB structure, and lo and behold, you repeat that over and over again, and voila, you have your graphene structure and your graphite crystal structure, HCP crystal structure. Again, very strong covalent bonds in this direction, very weak bonds in this direction. Key to understanding what's going on at the atomic level, all right? Now, it's a composite material, all right? Graphite is literally ground up pieces of graphite and coal and what we call filler material or graphitic flour that comes from either coal or a refinery of oil, all right? We then mix it up with a binder material, basically a pitch that you can put on your asphalt in your driveway. That's the same stuff. We mix it all up like a cake batter, we form it, and then we fire it, all right? So that's what's going on. It's a composite of these things, and the smallest pieces of that are made up of these anisotropic crystal structures. All right. These crystallites are in the, you're talking about nanometers at this point, where the crystallites and the forming up of the graphene planes and stacking them up. This is my language challenge for the day. This is a quinine insoluble particle, which is the benzene-rich precursor material for forming those hexagonal planes, all right? So that's what that is. Now we move up to the next length scale. these filler materials, the cake flour that I was talking about, turbostratic. And then you have these filler materials with this binder phase, the pitch that I was talking about. And look what you got here. Huge gas entrainment pores. And then finally you start looking at the greater microstructure. Remember, it's anisotropic at the crystallite level. It's isotropic when we grind it all up and we put it back into the cake batter. The macroscopic response is isotropic. Finally, we get to the components where we're talking meter size, all right, and how that responds to it. But during irradiation, neutrons interact with atoms, so we have to go back down to the atomic level, figure out what's going on at that point before we can understand what's going on at the macroscopic. Okay, so cute little cartoon. This is a ballistic damage event. Neutron comes in, it displaces a carbon atom, and it's just like a pool table. It blows out the atoms out of the crystal lattice. The interstitials come in between the graphene planes. They don't break those covalent bonds because they're too energetic. They go between the weak van der Waal. All right? Then you also have vacancies left over where you have just voids where the atoms were left over. So this is what's going on. You've got the neutron, it comes in, it blows the atoms out, they settle up, they form into these what we call subplanes, and voila, look, you have expansion in this direction and shrinkage in this direction because, you know, nothing like a void, nature of void, pores a void, it collapses. All right, so this is shrinking in the A direction, expansion in the C direction. This is the key to the macroscopic response. So you've got this going on at the atomic level, at the crystallite level. What you have is, remember I talked with you about the fact that they are processed, this graphite is processed at 3,000 degrees Celsius. Well, the thermal expansion is much greater in the C direction because of the weak bonding. So it swells. During cooling, when everything is rigid and brittle, it starts to contract, and as it contracts, it just literally opens up into these what we call Rosowski cracks. All right? So what's interesting is that under irradiation, it grows in the C direction and it closes these millions of Rosowski cracks. And so you never see it at first. It's hidden by the fact that you've got this pre-existing crack void that it's filling up for the first part. The only thing you see is the shrinkage in the A direction. Now, one thing that's a problem for me is that we don't see direct evidence of the shrinkage in the A direction. That's just assumed that that's what's happening. Okay. So let's look at it from a microscopic standpoint at the microstructure level. And we assume that the grains and binders shrink and swell similar to the crystallite length scale. There's no real mechanistic understanding of how the pores respond, though. All right? So we just ignore it. So we assume that there's no pores that are generated before turnaround, shrinkage, but pores are generated after turnaround as these crystallites and these grains start bumping into each other, and then they start forming cracks and voids in between the crystallites and the grains. As a consequence, you get only A-axis shrinkage right here because it's filling up those Rosowski cracks. The turnaround is when the cracks fill up, and this is what you see is when you see the C expansion going on. All right? Clear as mud? So that's what's going on under radiation. It's not what's happening at the atomic level. It's an accumulation of the different length scales to finally understand how the macroscopic response occurs. It's not a direct result of the atomic length scale. It's what happens as a consequence of the generation. Okay. Fracture, again, is dose dependent. It's dependent upon the dose level achieved before turnaround. Everything's compressive. You don't propagate cracks under compression. All you mechanics folks know that. And so at the lower doses, basically it impedes fracture. At the higher, and it also gets stronger, so again, you're getting less and less crack propagation or looking around. After turnaround, now you got tensile stresses that are occurring. You also have pore and crack formation, so you have crack initiation sites popping up all over the place. And plus, it gets weaker. So yes, graphite cracks after turnaround, and you can go and talk to the Brits right now, and the Brits can tell you, yes, indeed, their graphite bricks all have cracks, period. It makes for lively discussions with their nuclear regulatory system. Okay, and then of course the degradation of the oxidation can also lead to those types of things. I'm going to just go and real quickly breeze through this stuff because I don't want to bore you too much. But basically the irradiation strength and the thermal conductivity, what you see is these interstitial defects and the vacancy clusters. They pin any kind of dislocation movement, so it makes it stronger. And of course, the reason that it starts to decrease is because, again, you've got the pores showing up, and it just literally starts to fall apart from a strength standpoint. Thermal conductivity, the same thing. Point defects are interrupting the phonon transport through the graphite. Oxygen. Some of you will, I hope, like this slide. It's the last one. Basically, oxygen is not really affected by the irradiation. Oxygen only occurs on the reactive surface area sites on the edge of the graphene planes. It does not happen in the middle. So as a consequence, graphite does not burn. If there's one thing I want everybody to go out of this room with, is that nuclear graphite does not burn. It's not charcoal. There's no barbecues. Nothing can happen. It is like a large book. So anybody who's gone in, taken a large book, throwing it onto a kindling fire, does it burn? No. All it does is it may singe the edges, but the center of the book stays the same. Okay, you can still utilize it, much to our disappointment. As a consequence, the same thing for the graphite. Now you know why I'm a nuclear engineer. No, so the point is that you don't get anything hanging up or pulling off of those covalent bonds. Why? How could it? It would have to break an enormous number of covalent bonds for it to rip anything out of the center. It can only do it from the edges, and as a consequence, it only burns in one atomic length, and then it goes down to the next one, and it burns another atomic length. It can oxidize, but it can't self-sustain. There's just not enough reactive energy to keep it self-sustaining. Graphite cannot burn. If you want, I have actual videos showing that. Fission product transport, nobody really knows. We're doing studies as we speak. I don't really know what to say about this. Right now, basically, the irradiation disrupts the basal plane uniformity, but it really doesn't destroy it. So, you know, how the fission products diffuse through the graphite and the graphene structure, I just don't know. I don't think there's anybody out there who really does. We're performing experiments as we speak on this. Basically, studies continue. That's all I can say on that. Okay, so I'm about halfway, maybe a little bit more than halfway. What do we do to handle these challenges? Okay, we need to relieve the internal stresses from the dimensional change. Otherwise, it's literally going to tear itself apart. The longer we can delay it tearing itself apart, the less we have to replace the core. These cores are between $500 to $750 million of graphite. You don't change these things out lightly. The other thing, if anybody who's ever worked in a nuclear power plants, the rule of thumb, well, when I was your age, some of you, it was $1 million a day. That's how much they lost in revenue. Today, I think it's $2 million a day. You don't change these cores out lightly. You lose billions if you do. So the longer we can stretch out the time before we pull out this graphite, the better they like it. Also, we need to know what the risk is to have these things in the reactor. And that's, again, what we're trying to do. So we have to relieve the internal stresses. It's just a must. We have to understand how the fracture is affected by the internal stresses. We can't really stop the thermal changes, but we can have an understanding of the mechanisms involved in order, to determine the behavior. And then finally, can we produce an oxidation-resistant graphite? And the answer is yes. NASA did it. That's why the nose cone for the space shuttle is made out of graphite. Okay, creep. Creep in graphite is the key to longevity of the graphite cores. It is a misnomer. Those damn metal material scientists, they gave us the wrong word. What it really is stress relieving strain. Okay? As the stresses build up, the graphite actually displaces material, strains, and relieves those stresses. Okay? Like idiots, ceramic and graphite engineers took creep because it looks like metal creep, and it's just screwed us ever since. Anyway, so what's happening is dislocation flows in the graphite to relieve the stress buildup due to the dimensional change. All right, so creep is good for us graphite types. So again, because we're backwards. Okay, it keeps the graphite from tearing itself apart. The calculations are that if you had a graphite reactor, within about 3 or 4 months, it would literally have turned itself into large chunks. Another 3 or 4 months later, it would be about sand. All right, it literally tears itself apart without creep. Creep rate's affected by the temperature and the dose. Basically, the higher temperature, the higher the creep, more dose, higher creep. Creep is intimately tied to dimensional change. Without dimensional change, there is no creep. Without creep, it literally tears itself apart. It's the critical material property of your money that I am spending in your name. Fully 65 to 70% of the $100 million that's planned is going to look at this subject. Now, just to put that in perspective, UK is spending 120 million pounds to look at this problem. The Chinese are also looking at this. The Japanese have been looking at this for 30 years. Okay? Accumulatively, we probably will be spending $500 million looking at this problem. If that doesn't get your attention as capitalistic Americans, I don't know what will. All right? This is a huge problem, and we need to get our arms around it. Okay. Oh, and the reason is because we can predict the lifetime of the graphite components. Like I said, think about it, $2 million every day. If we stretch that out for 365 days, now you're looking at $750 million. So that kind of puts things in perspective. Okay. Postulated mechanisms understanding creep. So these small irradiation defects, remember these interstitial atoms in between and these specifically the vacancy clusters, well, what they do is they interrupt the dislocation flow, all right? Under irradiation, it blows these things out and rearranges the atoms and allows the dislocation to flow. It's called a pinning, unpinning mechanism. Now, this is the normal creep curve for a metal material, strain versus time and dose. You get your primary, your secondary, that's constant, and you get your tertiary creep. This is, we all thought we were smart as graphite folks. This is what we get after huge amounts of time and effort. The Germans kind of put this chart together. And you can see, if you close both eyes and turn around, you can sort of see a primary creep, a steady state secondary creep, and then a tertiary creep that goes on up. So we thought it was creep. Okay. Basically, the primary creep is very rapid. It's almost immediate. Tertiary creep begins after turnaround. It's associated with pore formation. Thinking we knew what we were talking about, we came up with a model saying, all right, we understand what's going on. We got a radiation-induced dislocation flow. The dislocation flows because of the radiation removing any pinning sites, allowing dislocation to move. It's a function of the temperature. It's a function of the flux. Therefore, we kind of understand what's going on. The assumption, though, is that we don't understand what basal planes are doing. It doesn't make any sense. They don't talk to each other. They don't communicate because it's weak van der Waals forces. It's only within the basal planes. So that's why we came up with this pinning, unpinning. It's only in these basal planes. It's a one-way street. There's no dislocation climb like you have in metals, we thought. No porosity considered. We're just, it's hard. And then tertiary creep, of course, is very hard to predict because of the pore generation and the need for the orientation of the crystals and the crystallites to understand how it's actually deforming over time. And this is what we get. And it's about the best we can get. And it's really nice. We get a nice short primary creep, and then we kind of get a secondary creep. I just sketched this on top. But what you can see is this is a viscoelastic, and what you see is you get a steady state creep, and then all of a sudden it just sort of peters out. It doesn't really match the tertiary creep. So we went in and have revised the model, and we can get it a little bit better, but it's not really all that great. Again, I told you I took rid of all the equations, and so what you get to see is pretty pictures. I have huge amounts of equations. If you want to be bored, I see a few people nodding off. This will put you under completely if you want. So obviously we need more information. Why is there no interaction between the basal planes? It doesn't make any sense. Is this truly what we see in microscopy work? All right, this eliminates climb-glide mechanisms, which is what creep is all about. It's getting the dislocations over those pinning sites. What is primary creep? It's not really, it doesn't make any sense. Again, it's a metal terminology where you have this metal pipe that's been pre-pressurized and heated up. We don't have that. And what is tertiary creep and when does it begin? Does it begin right when it closes, the Rosowski cracks close, or is it afterwards when the pores actually start to bump into each other? Okay, and then what about the other parts of the composite? What phase does the binder have versus the filler versus the crystallites? Downhill stretch, guys. All right, so this is unirradiated. You see these nice planes in the high resolution TEM. A little bit of dose, very small. You start to see, you still see the structure, but it's starting to get mixed up and disrupted. And then you get what this sort of a ruckling, buckling type of a process where it's literally starting to just destroy this beautiful page-like stack of graphene planes. And what's interesting is that they start to look like they're starting to interact with each other. Well, guess what? Some recent work out of Boise State shows that under at least TEM and the electron beam there, you do start to see some kind of interaction between the basal planes. Well, the model doesn't show that, but reality says it is. So as I said, folks, those of you who rely upon the textbooks, that they know what they're talking about, don't fool yourselves. It's written by us fools on the front line, and we get it wrong almost always the first time. We need to go back in. That's what science is all about, going back in or revising all of the assumptions. This is some models after we produced those basal plane interactions. This is some models that the University of Surrey back in the UK came up with, where they showed that, yeah, it's not energetically possible, but it can be done, where you actually have some bridging between the basal planes. Not very energetic, but when you're talking about million electron volts of energy smacking into these things from a neutron, anything's possible. Okay? So the models look pretty similar to what we see in the TEM images. And again, it's energetically not very favorable, but it is possible. Okay. So the microstructure changes are key to the tertiary creep. Again, what is tertiary creep? According to our current understanding, it's not runaway dislocation flow. Otherwise, it would just relax and these things would turn into silly putty over time. All right? It doesn't happen. What's really what we think is actually happening, it seems to be runaway dimensional change. Creep keeps up with it for a while and then finally it just pukes out. Okay? We can't, it can go in there and strain a little bit, but as soon as the C-axis, those Rosowski cracks close, then the C-axis takes off and we cannot keep pace with it, with the radiation creep. So that's what you're actually seeing on that tertiary creep. It's a different mechanism. We talk about dislocation flow for primary and secondary, but in the tertiary, it's a completely different mechanism. It's porosity. Okay, let's see if this works. Oh, technology. Thank you. So this is some work that we're doing at the INL where we're looking at X-ray computer tomography. Alex, so what we're looking at here is this is one gigantic pore inside of about a 3 by 4 millimeter sample. It looks like it constitutes a huge amount, but remember this is three-dimensional on a two-dimensional plane. So what you're looking at is this is actually only about 7 to 8% of the total volume. But it's all one interconnected pore. Think about that if you're trying to produce a crack through it. That's easy because of the connectivity. So this is my project. The Advanced Graphite Creep Experiment. 3 pairs of test capsules at 3 temperatures, 3 stresses, and over a continuous dose. By comparing the samples, each one of these holds about 500 samples, so we're talking about 3,000 samples, which is about the sum total of all the creep specimens that's ever been done historically. So it's a huge, huge effort by the United States to put a stake in the heart of this problem once and for all. So this is what's going on. These are the temperatures and the dose, and this is sort of what we're hoping to get. We want creep, we want strength, we want density, we want the conductivity, diffusivity, the stiffness modulus, and of course expansion as a function of dose temperature. So we can go in and get the creep rate as a function of the temperature, but we can also go in and get something like the strain that's going on. We can get the dimensional change. We can go in and start to get something as a function of the strain versus the temperature. Strain as a function of stress. We can also do this for all the other types of material. Biaxial fracture studies is another big program that we're working on. We are pulling, pushing at the same time. Different quadrants, internal pressure, tensile loading, and on. These are some of the results that we're getting. This right here should be out around in this area. The reason is because we had disparate flaws. We had these, in the graphite we were actually using, it was a fairly new graphite, and they hadn't quite gotten to production, and as a consequence we actually found somebody's shoelace in the graphite. Didn't work out real well for fracture toughness, but but they got it, they figured it out, and actually it works out pretty well. This is a later batch, okay? Improved graphite. We've done a small scoping study. This is what I showed you a few hours for normal graphite. You go in there and put a little bit of boron carbide inside there, and it forms a really nice protective coating, and you can see that it comes out to well plus 30 hours, okay? As a consequence, you get a 22% or 22 times decrease in the oxidation rate. It's pretty nice. It's kind of, again, the distribution problem is just because it's a new type of a process, but NASA figured it out. We can too. Finally, thermal changes. So what's interesting is that with a little bit of heat and a little bit of time, you can actually anneal out those point defects, and so the thermal diffusivity and conductivity starts to recover. How long? Well, most accident scenarios predicted for these kinds of reactors about 100, 120 hours. Well, you can get up to almost a 19% increase in the thermal conductivity that gets that heat out because you're not introducing more defects from irradiation. So wrapping things up, dimensional change is the big one. We've got to figure that out and how radiation creep affects it. Fracture, of course, is tied to the dimensional change and any kind of degradation. You can produce an oxidation-resistant graphite. The thermal property changes affect the performance of the core, and we need much more data, and we're getting it. I'm about halfway through my program, and I am putting in my 4th capsule in 2 months. So right now I have 1,500 samples that we're testing at this point. Some things I haven't talked about, dust generation. Basically, we consider that a sort of a pebble bed problem. I don't want to talk to you about that. If you know what that means, great. If you don't, come and ask me. Basically, it's not a graphite problem, but it can get contaminated with fission products. If there is a breach, you can have this dust cloud, which could act as a vector for the fission products. People are looking into that, but it's kind of hard to figure out if it's really a problem or not. Sample testing. How do we know when we take these small little samples that we put into the reactor really truly work with big, huge components? Makes sense. Chronic oxidation over the 60-plus year lifetime, it's different than the acute, folks. And there's going to always be a little bit of water, a little bit of air that's always trapped inside there. How does that affect it? And finally, this is the big one, non-destructive examination. Once we build one of these things, as the UK folks have demonstrated, there is a huge problem in figuring out what the heck is going on inside there. You can't stick a camera in there. It just fries it. You can't put anything inside there. How do you know when you have a crack? How do you know when you have a piece missing? Right? How do you know when you have an oxidation issue? That kind of NDE is critical for supporting the safety case for these reactors. And we don't have a good answer for it. And when I mean we, I mean worldwide. The UK is spending of that 120 million pounds, which is 2 to 1. They're spending probably 40 to 50 on trying to figure this out. And that's all I have.
Thank you very much for the interesting presentation. We have time for a few questions, and the presentation is recorded, so if you please identify yourself, so I'll come with the microphone.
So Will, your discussion focused on the graphite itself, but this is a composite. And some of the early pictures indicate that you have some cavitation, or at least the cracks at the interface between these, if I can call them grains, and the matrix. Can you comment on that?
Yeah, so the point is that these are manufactured pieces of material, manufactured material. So we take solid particles and we mix them with a liquid, and then we bake them. I mean, these are all terms that we use. Flour, binder, baking, okay, and bake out. What happens is we turn that liquid into a solid by deriving off the volatiles. And there is a necessary amount of gas entrainment in separation from the liquid to the solid, because you don't have complete intimate bonding. They mix it as well as they can, but obviously it's not perfect. And so as a consequence, you can get some delamination inside there. The bigger problem is probably the bubbles that form from the volatiles before they get enough pressure and they burst their way out. Okay, they actually form even worse problems because they're just larger cavitations inside there. So to correct that problem, a lot of people will what they call impregnate. They'll go in, put these things in the gigantic pressure cookers, and they'll heat up the binder material again, and then they'll drive it in as far as they can in through the open porosity, filling up those voids. They do that sometimes as much as 3 times to get it as dense as possible and fill up those voids that you were talking about.
So those are connected?
Yes. Yes, the porosity is connected from a gas entrainment bubbles, because obviously it's forming inside and it's making its way out to the exterior. Graphite, nuclear graphite is probably, and it depends on the grade, but I'm going to make a statement, it's about 12 to 15% open porosity. It's probably 8 to 9% closed porosity, with a roughly 20 to 21% total porosity. And before you say, well, hey, we could go in and make the porosity, that we will take the porosity out and that'll help. It won't. The real problem is that turnaround happens faster for dense material. You need that room to expand. Okay? Porosity, as bad as it is critical for the performance or radiation performance of these materials.
Given that in the manufacturing process you already have some techniques that change the properties of the, what else can be done? Suppose you'll take all these experiments that you have, you will definitely get useful information, but how can them be used in order to change the processing system?
Yeah, that's a fantastic question. In fact, that's what the whole program is sort of built on. What we want to do is, you got to remember, folks, when I talk about this material, it's as a composite, it's sort of historical composite. You've got people that swear that they have a better graphite because they have very small grains, 15 to 20 microns in size. Extremely small for graphite. You also have people that are sitting there saying, who cares about grain size? We're going to go in there and put it at 1.5 to 2 millimeters, 3 orders of magnitude larger. You have people that extrude it out like a Tootsie Roll. You have people that shake it or isostatically press it. You have different materials that they start, raw materials that they start with. What this program is designed to do, and I didn't emphasize it in my talk, is not just figure out what's going on currently, but try to understand what those manufacturing differences are and how they relate to the irradiation performance. So if it's large grain material that has a problem with irradiation, then we want to specify for future graphite types, go small grain, or vice versa. Same thing for the amount of binder versus the filler material, or even say the processing itself. Maybe extruded, which is an old-fashioned way of doing it, is the best way to do it. And all these other fancier, more expensive ways just doesn't work. So that's why we have 5 different types of graphite. They all come in different flavors, small to large grains. Some are isostatically, some are extruded, some have pitch versus PET, petroleum coke. All of those types of parameters for the fabrication are encapsulated in this experiment that we have.
Thank you. And I think we almost exhausted the time unless there is a last question. And if there is not, we can discuss at the reception. So you're all welcome to the reception. And please join me in thanking the speakers.
Thank you.